acids and bases. You can find most of the information for this in chapter 16 and 17 in your textbook. So let's start with what acids and bases are. A lot of this should be review, hopefully. We're going to focus on the Bronsted-Lowry definition of an acid and a base in this unit, which is an acid is a substance that donates a proton. A base is one that accepts a proton. They do not need to be aqueous. Most of the time we're talking about aqueous acids and bases. Most of the time we're going to be talking about the hydrogen ion attaching itself to water, so we're going to talk about it as hydronium. Water is amphoteric, so it acts as both an acid and a base. It can either accept or it can donate. And then going back and talking about those acid-base pairs, we have our acid, which is nitric, our conjugate base, which is nitrite. They lost to hydrogen or can gain a hydrogen. Our water in this case is acting as the base, and then the conjugate acid is H2O+. These are all at equilibrium. We've talked about this before. Nothing much different than what we've talked about before. A little bit different than that is the autoionization of water. So we're talking about water can actually act as both an acid and a base when it's pure water. So one water will donate its hydrogen, the other will accept. This does not happen at a frequent rate within a substance of water. Basically 1 out of 2 times 10 to the 9th water molecules. So if we look at it, we can think about that being an equilibrium constant, just like with unit 7. So we can look at Kw is equal to the concentration of our hydronium times the concentration of hydroxide. Remember, we don't include liquids in our equilibrium constants. So that is equal to 1 times 10 to the negative 14th at 25 degrees Celsius. This is a constant, so you will find it on your sheet, and you'll memorize this eventually because you use it so often. And obviously, with such a large negative value in our exponent, it's going to highly favor our reactants. pH and pOH are ways that we measure the concentrations of hydrogen or hydroxide. So pH is the measurement of hydrogen. pH is equal to the negative log of hydronium concentration. It's going to always be low, so the lower the pH, the more acidic it is, the higher the pH, the more basic. That is exactly the opposite for pOH. We find it exactly the same way, but using hydroxide. Low pOH is basic, high pOH is acidic. So when it's neutral, pH is equal to 7, and pOH is also equal to 7. We can also look at the fact that 14 is equal to pH plus pOH, so we can always use those to find each other. More on pH and pKa's, so we can look at the equilibrium constant and find the negative log, and we can get pKw, which is also equal to pH plus pOH, which is equal to 14. So all of these values can be used to find each other. They're interchangeable equations. So let's look at a quick practice. We have a sample of freshly pressed apple juice with a pOH of 10.4. We're going to calculate the hydrogen ion concentration. This, we can find 2 different ways. The first way is to say, is to know pH plus pOH is equal to 14. So 14 minus 10.24 is equal to pH. Which is 3.76. And then we could take that and say pH is equal to the negative log of the concentration. Remember, we were talking about concentration, we must use brackets, of hydronium. So we can work our way backwards, and we know that the concentration of hydronium is equal to 10 to the negative pH. So 10 to the negative 3.76 is equal to 1.74 times 10 to the negative fourth molarity. Okay? So when we're talking about negative log, we're talking base 10, negative log if I hadn't talked about that before. So our second way is we can say POH is equal to the negative log of OH concentration. So we know 10 to the negative 10.24 is equal to 5.75 times 10 to the negative 11th. Then we could say Kw is equal to the concentration of OH times H3O plus. So we can solve for H3O plus because we know Kw is 1.0 times 10 to the negative 14th, because it's at 25 degrees Celsius, or we're assuming at 25 degrees Celsius, and we would divide that by 5.75 times 10 to the negative 11th, and that is going to equal 1.74 times 10 to the negative fourth. Looking at pH and POH of strong acids and bases. Make sure you are not mistaking concentrated for strong. Concentrated is talking about the amount that there. Strong is talking about how much dissociates. So a strong acid will completely disassociate or completely ionize, where a concentrated acid is going to have a lot of starting material. So make sure we're not mixing those two up. You need to memorize these strong acids, strong bases. We've talked about them before, but it's really important that you just know when you look at the list which one are strong and which one are weak, because they're not going to tell you. So hydrochloric, hydrobromic, hydroiodic, nitric, chloric, and sulfuric are all strong acids. Our strong bases are the alkalis and our alkali earth. Okay, so sodium and potassium are two strong bases that we use most often, but lithium fits in there too. So anything with the alkali metals, and especially the heavy alkaline metals. So let's look at a practice problem. What is the pH of 0.04 molars of chloric acid? So this chloric acid is one of our strongs. So we just know that when we have chloric acid, it is going to completely disassociate into the chlorate ion, it's negative, and the hydronium ion. And we know that because it's strong, so it completely disassociates. So we also can see from this that it's a 1-to-1 ratio. So the concentration of our our chloric acid is equal to the concentration of our H3O plus, our hydronium. So this makes it an easy one. pH is equal to the negative log of H3O plus. And we know the concentration of H3O plus is equal to the concentration of HClO4. So we can just say negative log of HCO plus is going to be 1.3979. Strong because it's close to 1. Okay. What is the pH of our sodium hydroxide? This is a strong base, but we're looking at hydroxide ion, but we want to find pH. So they're going to have to go through two different ways. We either going to figure out using our two different methods. We have POH is equal to the negative log of our concentration which is equal to 1.55. And then we could say 14 minus 1.55 is equal to 12.45. Okay, so that's our first way, because we know pH is plus POH is equal to 14. The other way we can go about it is we know that the Kw concentration of hydronium times the concentration of hydroxide. So we know 1.0 times 10 to the negative 14th is equal to hydronium ion concentration times our concentration of our hydroxide, which is 0.028, because it's a 1-to-1 ratio. And we end up with H3O plus concentration is equal to 3.57 times 10 to the negative 13th. So negative log of this value is equal to 12.45. Okay, so it double checks itself. Last but not least, we're going to look at the fact that pH of a calcium hydroxide. Now in this case, it's not 1-to-1 because we have calcium hydroxide. We have two hydroxides here. So when we go to completion, we're going to have calcium 2+ ion, and we're going to have 2 hydroxide ions. So basically for every 1 calcium hydroxide, we have 2 hydroxides. So basically the concentration is doubled. So we take 0.0011, multiply that by 2, and we get 0.0022. And we can do the same two structures, but I am just going to do negative log of 0.022 is equal to 1.66. And remember, that's the POH, and we want to find pH. So 14 minus 1.66 is equal to 12.34. And we get our concentration, or sorry, our pH of that concentration. Bases at equilibrium. So we're going to think back to Unit 7 and our equilibrium expressions that we used there and apply it to acids and bases. So a weak acid is considered weak because it doesn't completely dissociate, unlike a strong. So we have an equilibrium being established. Our concentration of our initial HA acid is not going to be equal to our hydronium concentration. All right, HA is just a substitution that we use for a weak acid. Very little of our acid is going to ionize, so we can create an equilibrium equation, which gives us an equilibrium expression of Ka is equal to the concentration of hydronium times the concentration of our ion divided by the concentration of our acid. Notice that we do not include water. Water is the liquid. And again, we can find pKa from this. Whenever we think about acids and bases, we can look at the negative log scale because it actually is much easier and simpler to think of it in the log scale. So let's look at a practice. So we have a 0.1 molar concentration of formic acid, and it's at pH is 2.38 at 25 degrees Celsius. So we're going to find the Ka. Well, to find the Ka, we have to start by finding the concentration and then using an ice table. So, concentration of our H+. We look at it and we can find that because we know it's our pH. Our pH is equal to the negative log of hydronium concentration, or our H+ concentration. Those are interchangeable. So we know that our concentration of H3O plus is equal to 10 to the negative 2.38 which is 4.17 times 10 to the negative third molarity times, right there. Okay, so now we can just create our ice table. So our reaction is formic acid reacting with water to form our hydronium and our formate ion. We're not going to worry about water, so I'm not going to make a... All right, our initial concentration of our acid is 0.10 molarity, and then this is going to be A, at equilibrium, our change, and then we have equilibrium. And we know our equilibrium concentration because we have our pH. And our pH is based upon our equilibrium concentration. So we know that it's 4.17 times 10 to the negative third. And it's a 1-to-1 in our equation. So it's also 4.17 times 10 to the negative third. So that means our change here is 4.17 times 10 to the negative third positive, and also here, and our change here is minus 4.17 times 10 to the negative third. So we take our concentration of our acid, subtract 4.17 times 10 to the negative third, and we get 9.58 times 10 to the negative second. We put our three values into our Ka table, Ka expression. So we do 4.17 times 10 to the negative third, and we multiply it by 4.17 times 10 to the negative third, because we have our hydronium concentration times our ion concentration divided by our initial concentration of our acid, so our equilibrium concentration of our acid, which is 9.58 times 10 to the negative second, and these all should have molarity here. And doing the math, we end up with 1.81 times 10 to the negative fourth. And that's it. Weak base is a similar concept to the weak acid, right? But we're talking about hydroxide instead of hydronium. So our hydroxide concentration is not equal to our base concentration. We use the same exact equation, but we're talking about Kb versus Ka. So we substitute in B's instead of A's, essentially. All right, and then we have calculate the concentration of OH minus in 1.5 molar solution of ammonia. We are missing one thing we need to know to be able to figure this out, and that is the Kb of our ammonia. Which is 1.8 times 10 to the negative fifth. So using these two values, we can actually figure the concentration of OH minus. So we need to figure out, so remember Kb is going to be equal to our concentration of OH minus times our concentration of NH4 plus all over our original base, which is NH3. I know that because we go NH3 plus H2O. Remember, a base is a proton acceptor, so it becomes NH4 proton accepted and OH minus. Okay, so it took its hydrogen from the water. All right, so we need to solve for our concentrations here. So we can figure out our concentrations doing a ice table. Initial change equilibrium. And remember, we're just going to ignore our water. It's a liquid, so it doesn't matter. Our initial concentration of our base is 0.15. Our conjugates, our ammonia and hydroxides are 0. The change is going to be minus X and plus X. And we know that this X is going to be negligible because it's going to be so small in comparison to 15, so we could just keep it out. But this is going to be X, and that's going to be X, so we can put it into our equation. We have 1.8 times 10 to the negative 5th is equal to X times X divided by 0.15. 1.8 times 10 to the negative 5th divided times 1.5 or 0.15, which is equal to 2.7 times 10 to the negative 6. I have it written down next to me. Okay? And we got to solve for x, right? So x squared is equal to 2.7 times 10 to the negative 6. So we square root those. And that is going to equal 1.6 times 10 to the negative 3 molar. And we know that's equal to x, and x is equal to both ammonia and hydroxide, ammonium and hydroxide. So this is our final answer. Last but not least, when we're talking about this, we could talk about how much of our equation has been ionized. So we know percents are just timesing it by 100. In this case, we're going to look at concentration of ionized divided by the original concentration of either our acid or our base times 100. So let's look at a practice. We have our concentration of hydrogen ions. I put the KB on the wrong page. That should have been on the previous page. So we have a concentration of our hydrogen ions is 4.2 times 10 to the negative third, and our concentration of our initial acid solution is 0.1. So we just take 4.2 times 10 to the negative third molarity divided by 0.10 molarity times 100 equals 4.2 And that is it. That is the entire way to find percent ionization. Acid-base reactions and their buffers. Strong acids with a strong base. So when we react an acid with a base, we call these a neutralization reaction. And generally when we have a strong acid with a strong base and they're reacting with equal molar, they're going to cancel each other out and you're going to get a neutral solution. They're always going to form a salt with the water. So we got hydrochloric acid, sodium hydroxide, yielding salt and water, and this time really salt. The net ionic for a strong acid, strong base is always going to be the hydronium plus the hydroxide yielding water. pH is always determined by which one is in excess, and so it becomes a dilution question. We're trying to find the pH of a strong acid, strong base reaction. Obviously, if it's at equality, if they're equal, then it's neutral. More acid is going to have a low pH, higher acid is going to have a high pH. Technically at equilibrium, but not really because the solutions so greatly favor the products. All right, so let's look at a question. We have, what is the pH of a solution that is created combining 25 milliliters of 0.212 molar hydrochloric and 45 milliliters of 0.2 molar of sodium hydroxide? This becomes just really a straight-on dilution question where we're using that equation M1 V1 equals M2 V2. And we're going to have to do dilution for both of them so we can discover which one is going to be in excess when they're together. So we have our molarity of our acid and our initial volume. We're trying to figure out what our molarity is after our two solutions are combined. So our new volume is 25 plus 45. Doing the math, I end up with a molarity of 0.043 molar. Same exact thing for NaOH. We have our molarity, initial volume equal to our combined solution molarity and our new volume, which is the volume of each of our substances that we combined. Our molarity for sodium hydroxide and we can see without even looking, there is a higher molarity of sodium hydroxide to hydrochloric acid, so that means there's more moles. And if we look at the equation of hydrochloric acid with sodium hydroxide, we know it's 1-to-1. So that means for every 1 molar of hydrochloric, we need 1 molar of sodium hydroxide. So that makes it easy to look at which one is in excess. We subtract the two. You could set it up as an absolute value, or take the larger number and subtract the smaller number from it. And we're going to get 0.087. So this is how much excess sodium hydroxide we have. And so our new solution is going to be based on the excess of sodium hydroxide. So we just do negative log. Because remember, we're trying to find pH. 0.87. We get 1.06. And remember, that's POH because it's the sodium hydroxide. So we just take 14 minus 1.06. And that's 12.4. So our pH of our new solution is 12.4. It's a very similar idea with weak acids and strong bases, or even weak bases and strong acids. It's still going to be the acid-base reaction where we're getting salt and water, but when we talk about in a net ionic, we're going to look at the fact that it's going to have that acid plus the hydroxide yielding the conjugate base of our acid and our water, because in this case the weak acid is not going to fully deionize, and so we get into equilibrium. The hydroxide ion, obviously the base, fully ionizes. So we now are looking at an equilibrium reaction. Looking at equilibrium, we're going to have to use ice tables. We're actually going to learn a shortcut how to figure out a weak acid is in excess using something called the Henderson-Hasselbalch, but we need to be able to also identify how to use an ice table with this as well. So we're going to first start off with just using ice tables. So if the weak acid is in excess, we're going to use an ice table. Focusing on the equation, HA plus water is yielding our ion and our hydronium ion, because really if this is in excess, the hydroxide gets used up completely and we're left with our equilibrium of just our acid, our weak acid. Now if the strong base is in excess, the pH is determined by just the base because it's used up completely that acid, so we're no longer at this equilibrium. And then finally, if they're equimolar, we're still going to have this equilibrium, but the focus instead is going to be on the base, because the strong base is going to push our reaction towards the base, because it disassociates completely, whereas our acid is not going to. So it's going to be important to know which one of these equations we're going to use depending on whether we have excess acid or excess base. And remember, we're first doing dilutions to figure out which one is in excess. So, weak base, strong acid, same exact thing, just similar concept, just reversed, where weak base is in excess. We can use the Henderson-Hasselbalch eventually, and if the strong acid's in excess, the pH is by the acid, and then if they're equal, it's going to be a equilibrium with the focus on the acid. Weak acid, weak base is a 100% an equilibrium reaction, and we're going to use ice tables. So trying to use Ka to solve for pH, because when we're using ice tables for the equilibrium, we have to use either the Ka or the Kb. And we're going to use the equilibrium expression of the ionization of the weak acid, if that's what's in excess, or the weak base, if that's what's in excess. And obviously we're going to be doing a dilution to figure out which one. We're going to do the ice tables, and then we're going to solve for x. So let's walk it through. Alright, so first we start off with our dilution. I'm going to do it up here so I have room for everything else. We have our hydrofluoric acid in our original concentration. We have our new concentration in our new volume. And that is 0.077. And we do the same thing for our strong base. Alright, so we have to first make sure before we decide which one is in excess, if it's a 1-to-1. So we have our reaction. And we're going to get NaF and water. And as we can see, it is 1-to-1. So we can just subtract these two values to figure out which one is in excess, which we could just look at it and obviously see that there's more hydrofluoric, so that's in excess. So we take 0.077 minus 0.071, and we get 0.006 of hydrofluoric acid. And that is our weak acid. So our equation is going to focus on the acid. So we have our dissociation of our acid. So we got to make our ice table for that. Remember, we're not worried about water, so we could just take that one off. It's just a liquid. So our initial concentrations are going to be based upon up here. So our initial concentration of hydrofluoric acid is what we calculated after the dilution. Now, this is how much sodium hydroxide we started with. It's going to react until all the sodium hydroxide is made into water and sodium fluoride. So the amount of sodium fluoride we have is how much sodium hydroxide we started with, because all the sodium hydroxide becomes sodium fluoride, and we have 0 of hydrofluoric to start with. So the change is going to be plus A. Oh, sorry, this should be minus A because we're losing it. And this should be plus A. And our equilibrium concentrations are going to be plus A, 0.071 plus A, minus A for the reactants. And this is just going to be A. Well, our A is likely to be too small to matter, so we're going to take it off these two parts, and we're just going to put it into our equilibrium expression. Remember, it is products times reactant divided by reactants. So we are missing one thing, and that is our Ka value. That looked up is 6.6 times 10 to the negative 4. And so we solve for A. A is going to be 5.07 times 10 to the negative 5th, which is equal to the concentration of H3O. So then to figure out the pH, it's just the negative log of the concentration of H3O. And so our pH is 4.29.